So in the last class, we have just started solving a problem. So we'll continue with that problem today also. So most likely today and the next class also will be solving problems uh, and we'll conclude this particular module. Okay. Here that slide. This the problem statement we have seen yesterday. There's a thin-walled pipe, uninsulated thin-walled pipe of 100 millimeter diameter is used to transport water to equipment that operates outdoors and uses the water as a coolant. So this pipe carries water and particularly harsh winter conditions, the outside wall of the pipe has achieved minus 15 degrees Celsius. And inside water is flowing, which means that the temperature is above 0 degrees Celsius. So outside is minus 15 and inside is 0. That means the temperature is transitioning from positive value to a negative or 0 value to a negative value. No, not 0 value, sorry. The water is at 3 degrees Celsius in the center and the wall is at minus 15 degrees Celsius. That means there is a transition of temperature from a positive value to a negative value, which means somewhere in between there should be a 0 degrees Celsius. And we know that water freezes at 0 degrees Celsius. So we are told that there is a cylindrical layer of ice forming. We are asked to find out what is the thickness of the layer of ice. So this entire problem was shown schematically here. So this is the pipeline that carries water at 3 degrees Celsius, and this flow of water is associated with a convective heat transfer coefficient of 2000. And on the surface, the temperature of this pipe reached minus 15 degrees Celsius. So because of this change in temperature from positive to negative, there is a possibility of ice formation. So there is a cylindrical layer of ice forming at 0 degrees Celsius. So what is the thickness of ice? So this thickness of the ice layer that has formed, that is what we have to find out. So this cross section, if you see from the side, you will see like this. There is a R1 is the inner radius, R2 is the outer radius, and R2 minus R1 will give you the thickness of ice. So we have to find out the value of R2 minus R1, out of which we know R2 is given in the problem as a 100 millimeters diameter pipe. So R2 is 100 by 2 is 50 millimeters. So this is where we stopped yesterday. So let us continue from here. Now, how to solve this problem? Firstly, let us identify what are the modes of heat transfer that are involved here. So we can see that at the center there is some flow. Fluid is flowing, water. A fluid is flowing, therefore there will be convection, and rightly so we are given this convection heat transfer coefficient which we can use. Also, there is this solid ice that is formed, and when it is solid, the form of heat transfer associated with will be conduction in this region. Therefore, heat convected from this region to this region, sorry, heat convected from this region to this region will be equal to the heat conducted across this layer of ice. So that is the kind of energy balance that will be needed to solve this particular problem. So we'll do that and try to solve this problem. So we'll write an energy balance here. What we do is energy balance at the ice water interface. So this is water, this is ice. So in this region, this is the interface, heat convected uh, by water should be equal to heat conducted in ice. That's the energy balance for steady state conditions. So for this, we know the formula. Heat convected is the Newton's law of cooling, and in this one we can use the Fourier's law of heat conduction. Okay, so these are the equations that we need to use. So on the left hand side, we will use Newton's law of cooling, H A delta T is the basic form, and for the right hand side, the Fourier's law of heat conduction. General, we can write it as a delta T divided by R. The overall temperature difference divided by the resistance. So temperature difference in the ice, and R is the thermal resistance of ice. So this is what we can do. And now let us try to substitute the values. H is given as 2000 multiplied by area. Area through which heat is transferred is this area along the entire length. Okay, so this is circumferential area 2 pi r1 L. L is the length of the pipeline. So for the sake of this particular problem, let us consider unit length. Since length is not given, we'll consider the unit length. So L can be taken as 1. So this is H, this is area multiplied by delta T. Delta T will be T infinity minus Ts1. T infinity minus Ts1, this surface temperature. So this should be equal to this on the right hand side we have the heat conduction, and for this we will use the heat conduction formula for cylindrical coordinates. So for a cylindrical shell, we know that the heat transferred is the overall temperature difference divided by the resistance. So this overall temperature difference will be Ts1 minus Ts2 divided by the resistance is 1 by pi KL logarithm of R2 by. So this formula, we have derived it, we have seen it earlier. So this formula is available in data book page 53. Okay, so this is the basic equation that we will be going ahead with and solving the problem. Okay, so this is 2000 multiplied by 2 pi. Now R1 is something we don't know. We have to find R1. R2 is known to us, but R1 is not known. So R1 multiplied by L, we'll take it as 1. Multiplied by T infinity is given as 3 degrees Celsius. T minus Ts1. Surface temperature, this is ice. So this is ice at 0 degrees. So this should be equal to Ts1 minus Ts2. So this surface is S1, this surface is S2. So this is across which conduction is taking place. So this is 0 and this is minus 15. 0 minus of minus 15 divided by 1 by 2 pi K. K is the thermal conductivity of this surface. Surface. Now this is ice, and for ice, K is, we are not given this value in the problem, so we'll have to find it from the textbook, data book. So where to find this value of ice, conductivity of ice in the data book? You can refer to page 16 of the data book. You'll see that at 0 degrees Celsius, conductivity of ice is 1.88. So this is from page 16 of the data book. Now this is from page, this formula is from page 53 of the data book. So K is 1.88. That's what we'll take. By logarithm of R2 by R1. R2 is known to us, that is 50 millimeters. So it will be T multiplied by 10 power minus 3 divided by R1. So you can see that we have taken R1 and R2 in meters. So this R2, which we have as 50 millimeters, is converted to meters. 50 millimeters is given to us, converted to meters by multiplying with 10 power minus 3. That means R1 here, they are in meters. Okay, so that's how we need to interpret. Okay, now let us simplify this equation. On the left hand side, we have uh, 37680 R1. On the right hand side, we will have divided by so you can see that we have one equation in R1. Left hand side we have R1, right hand side also we have R1, but it's at the logarithm. You can try to simplify this a little bit further. Now this you may try to solve in different ways. It's a little bit tricky because this is not really a linear equation. So from this, actual idea is to find what is R1. Okay. So finally, the equation that we are left out with is 12.76 R1 is equal to by log of 3 into 10 power minus R1. Okay, now one way of solving this, see some calculators may have this facility to solve this right away. Okay, but any computer in general will follow what is called as an iterative method, or sometimes it's also called, it's also turns out to be a trial and error method. Now you know here the diameter, outer diameter of our pipe is 50 millimeters, and therefore R1 can be anything less than 50. It can be 40 millimeters, it can be 30 millimeters, it can be 45 millimeters, 48, 49, and so on. So we have to do a trial and error. So one way of doing it is try different values of R1, substitute on the left hand side, substitute on the right hand side, and see whether it satisfies or not. Okay. Now that is one way of doing it. Other way of doing it is what is called as a iterative method. So you assume a value of R1 here and compute a new R1 using this, and keep updating this value of R1 as long as this R1 does not change any further. So that is what every computer does. Now I would like to demonstrate that using Excel. So the same procedure I'll show you using Excel. So that is basically what you will need to do manually also. Okay, now I will change the value of R1 and I will compute the function. This is the function I'm talking about. The function, you have seen one equation in R1. So the left hand side and right hand side, if you bring them to the same side, then that will be the function. So R1 can be changed from, let us say, 1 millimeters, 10 in steps of 5, 15, 20. In 9, let me not go to 50 because 50 is the maximum function. The function is, I'll just show you this, what function right here in the Excel sheet. The function I'm going to write is 212.76 R1 minus 1 by log of t multiplied by 10 power minus 3 by R1 is equal to 0. So this is the function I am going to write, and I will see where at what value of R1 this function becomes equals to 0. That will be the root of this function, and that will be the value of R. So that is what I will do in this Excel sheet also. Now let me see the function here. 212.7. R1 divided. See, these values of R1 are in millimeters. So I am converting to meters. Okay. So I have computed the value of this function from a range of 1 to 49 millimeters. R1 I am taking. Now you can see here. Are you able to see this Excel sheet?
Yes, sir.
Okay. Now you can see the value of this function up to 45 millimeters. It was positive. See here, the value of the function is changing. It's a positive, and at 49 it became negative. Now you can see here why I have plotted this function. I have calculated this function. I select these values and try to plot a graph. You can see here in this region between 40 and 50, about this, it is becoming 0. You see where the value on the y-axis at this point it is 0. That means below this it is above 0, and above this point it is below 0. That means the root is somewhere here. And from these values we can see that the root is between 45 and 49. So what I do is I will compute this much further, at different, much different values, 45, then I'll say 46. Oh, now you can see it is between 45 and 46, it is changing. So let me keep increasing in a much finer way from 45, 45.1. Now you see 45 and 45.1, in between this it is minus 0.1. So it is changing from 45 to 45.1. So it'll take much smaller value, uh, lower than 45.1. So 45 point positive, 45.02 positive. See, you see here, 45.04 positive value, 45.06 negative value. That means you can very confidently say that it's between 45.04 and 45.06. So the root we can say is 45.05. So the R1 value is 45.05. So that is what you can conclude from this particular analysis. So you can see here at this point, at about 45.05, it is becoming equal to 0. So that is what you can understand from this. Okay. Did you understand what I have done here? The equation, why I have to do all this exercise is because the equation that we have taken up or that we had ultimately after writing the energy balance is a non-linear equation. It has got logarithms, and you can try to solve it. It may not be so straightforward to solve. Therefore, I have chosen what many engineering solvers do. What they do is go for a iterative method or a trial and error method. What I have done is similar, except that initially by taking a, a, a what you call course values from R1 1 to R149 in steps of 5 millimeters. I have calculated the value of the function, and I understood that between 45 and 49 it is turning uh, to be the root. The root lies between 45 and 49. Then after 45, I have made finer increments. You see 45, 45.01, 45.02, 45.04, 45.06. From this, you can see that the root lies in between 45.04 and 45.06. So that is where I have concluded that the root is 45 millimeters. So this is how you can solve this particular problem. So you can, this exercise you need to actually show it, this working you need to show when you're solving, and then you can write on solve on solution. R1 will be 45.05 millimeters. Therefore, thickness of ice 50 minus 45.05 is almost 5 millimeters. So this much thick ice will form. So the answer is given as 5 millimeters. That's because the value of the K value, what we have taken is 16. We take a slightly different value because in the same data book, if you refer to another page, I'll show you. In page 16, the value of ice at 0 degrees Celsius, conductivity of ice at 0 degrees Celsius is taken as 1.88. Okay, in a different place, the ice conductivity in page number 21, the conductivity of ice is taken as 2.25. So 1.88 was what we have taken, 2.25 is what is given here. So depending on what exactly you take, so the conductivity of ice can also change depending on the source of water. So If you take a slightly different value, you may get 5 millimeters. Ultimately, what we got was close to 5 millimeters, 4.95 millimeters. So this is how you need to solve this particular problem. Okay. All right. Now we'll take up the next problem. A plain wall of thickness 0.1 meters and thermal conductivity 25 watt per meter Kelvin having uniform volumetric heat generation of 0.3 megawatt per meter cube is insulated on one side while the other side is exposed to a fluid at 92 degrees Celsius. The convection heat transfer maximum temperature. So this problem is related to steady heat conduction, heat generation, one-dimensional steady state heat conduction involving heat generation. Generation that we are seeing here is 0.3 megawatt cubic meter. So let's solve this problem. Plane wall of thickness 0.1. Having uniform volumetric heat megawatt per on one side, the other side is exposed. Let us say this will take it as a right side. This is the insulation. The other side is exposed to a fluid at 92 degrees. Heat transfer wall and the fluid. This is the maximum temperature. So in the entire domain, what is the maximum temperature?
Excuse me, sir.
Yes.
So your voice cannot be heard in between. In intervals, it's stopping. So I don't know. It's a problem at my end.
I don't know. What about others?
Yes, sir. Same problem, sir.
Voice is little low, sir.
Okay. Let's speak louder. See, continuous. Let me know. Okay. So we have this T max to be found out. Maximum temperature in the entire region. Now we have seen two situations of the problems involving heat generation. Okay, so first thing is we had a slab with same temperature with symmetric boundary conditions Ts and Ts with some heat generation. So for that the temperature profile was something like this. There's a peak. So that peak, if the conditions are symmetry like shown in this picture, the peak will be at the mid plane. So this will be the peak and this will be the maximum temperature. And at this point, dt by dx will be equal to 0. So that behaves as an insulating condition. And we have seen another situation also where the slab is subjected to asymmetric conditions. So this is, let us say this is TS1 and this is TS2 and there is heat generation. Because of the asymmetric conditions, TS1 is not same as TS2 and if you assume that TS1 is greater than TS2 and with heat generation, then the temperature profile will be something like this. So this peak will not be at the center, but it will be somewhere off center. Is at this option. So this is the peak depending on the asymmetric conditions. But the point is wherever the peak is at this point, at this point or at this point, dt by dx is equal to 0. Okay. So what is the meaning of dt by dx is equal to 0? There is no thermal gradient. When there is no thermal gradient, what will happen to heat transferred? Q, heat conducted Q. Q is equal to minus K A dt by dx, isn't it? If dt by dx is equal to 0, Q will be equal to 0. That means wherever this thermal gradient is 0, it behaves as if the surface is insulated. We are actually not insulating. We don't have to insulate, but we have this condition that wherever the gradient is 0, it is insulated, or wherever it is insulated, the gradient is supposed to be 0. So in this case, gradient is 0, therefore Q is 0, insulated. In our problem, it is insulated, so Q is 0, that means dt by dx should be equal to 0. Okay, so that is where that is the point which we will be using it. Okay, so therefore, the point I'm trying to drive is this dt by dx will be equal to 0 at a point where the temperature is maximum. Okay, so T max is at the insulated phase. Therefore, in this problem, T max will be somewhere, maximum temperature will be here. So the temperature profile will look something like this. This should be the temperature profile with the maximum at this point. Okay, so now we will use the equations that are available for us to solve this problem. We have derived this during the theory. Now we will use this. Now we have steady state heat conduction with heat generation, and for that we have for outside conduction conditions. So I'll write the equation here. I am referring to page 56 of the data book. In page 56, we have one equation, TW. What is the wall temperature? TW is equal to T infinity plus Q dot L by H. T infinity is the fluid temperature, Q dot is the heat generation rate, L is the thickness of the slab, and H is the heat transfer coefficient. So this is what is given in the data book. In our case, we will call this temperature as this. Let us call this as TS2, and let us call this as T max or T naught, whatever it is. So this T in place of TW, I substitute TS2 is equal to T infinity plus Q dot L by H. So T infinity is 92 plus Q dot is 0.3 mega. So I will convert it to normal units, 10 power 6 into 0.1 divided by H is 500. Compute this. So this will be 152 degrees Celsius. And now the problem asked is to find the maximum temperature. So the maximum temperature is at the center, is at the insulated surface. So we have this equation here, the data book, the same page of the data book, we have T naught, which is same as a T max, equal to TW plus Q dot L square by 2K. So this will be T max. T wall is a TS2 plus Q dot L square by K. So TS2 I'll substitute as 152. Count that out. Q dot is 0.3 multiplied by 10 power 6 multiplied by L square is 0.1 whole square divided by 2 multiplied by 125. So this will be 212 degrees Celsius. So I hope you are following the data book also. I am writing the page numbers wherever I take the data or use a particular equation. This will keep continuing. In fact, when we go to convection, this kind of a referring to the data book will be quite often. Will be very often done. So please get used to it as soon as possible. I see there's a message. What is that? Somebody is trying to message. Okay, my voice is too low. How is it? How is the voice now? Did it improve or continue to be same?
Sir, now it's okay, sir, but sometimes like the voice goes almost on mute, sir, like that.
Oh, no, maybe sometimes I'm not even talking. Because I may be computing, I may be using the calculator. At that time, I may not be talking. So at that time, you may not be hearing. Or if you think the voice is breaking, then let me know, okay? Because there could be a few seconds when I'm not actually talking at all. Anyway, for today's class, that will be enough. Now, as I said, let me introduce you to this particular software called as the interactive heat transfer. So yesterday I gave you the link for that. I hope you have downloaded the link. Did you? Did you download that software and install it?
Yes, sir.
Okay. Now this is the software and this is the interface you see with the software. Now you can see the tools available here. The first button on the left is called as the solve button. That means once you write a little bit of equations here and don't say code, you write the equations just like you write the equations in.
Yes, sir.
Yes.
I don't know if it's from my end. I can't see your screen, sir.
Okay, am I not sharing? I'm sharing.
It's showing black for me.
Yeah, your screen is not visible,
Yes,
sir.
sir, for me too, sir.
I'm not able to see my
Yes,
interactive.
sir. Screen is not visible.
So what are you seeing right now?
So it was just black screen, sir.
The software is it says I'm presenting. What about now?
It's still the same, sir.
No,
It's a tricky thing now. I don't know what to do. Have you downloaded the software? Anyone?
Not yet, sir.
So anyway, I'll give you the link once again so that you can download and install it. We'll have to figure out how to overcome this problem. So I posted the link here. Those who missed it yesterday, you can download it now and install it. It's a free software. It actually comes along with the textbook of heat transfer by Incropera and David. I will try one last time. How about now?
No,
Anything?
Sir, only your icon is visible, sir. Software is not visible, sir.
What icon?
Your like my MS Teams icon, only that is coming, sir.
Oh, this is what you're seeing. Yeah, that's tricky.
sir.
So what to do with this? Is it possible to share the entire screen?
So maybe just try sharing your PPT. Let's verify that it's not an internet issue.
Shared my presentation.
yes, the presentation is visible.
Okay, so this is coming.
What's the problem with the software?
So I think sharing full screen should work.
Where is the option for that?
So I think when hitting share, there's options either to choose which program or your full screen as such.
I think, sir, it's shown as share your desktop. I think so.
But I never saw that share your desktop in MS Teams.
So it says